I'm Dr. Denise Hurd, Director of Research for the U.S. Poultry and Egg Association. Today, I have the pleasure of speaking with Dr. Stephen Spatz about one of his highly anticipated current research projects funded by U.S. Poultry and its foundation. Dr. Spatz is a microbiologist for the United States Department of Agriculture, Agricultural Research Services, Southeast Poultry Research Laboratory. Welcome, Dr. Spatz. Congratulations on your funded research project, and thank you for sharing your research with us today.
Well, thank you for the invitation, and thank you for the USPA and the Foundation for funding my grant. I really appreciate it.
So, Steve, your study titled Development of mRNA-based Vaccines for Protection Against Disease Caused by Infectious Bronchitis Virus and Infectious Laryngotracheitis Virus has been causing quite a stir within the industry, as so many are excited for it to get underway. Can you begin by providing a brief overview of your project and explain why you feel it is a need within the industry?
Sure. Well, we know that infectious laryngotracheitis and infectious bronchitis viruses are two important pathogens in the poultry industry. So we'd like to use a kind of novel modern approach on just making vaccines based on RNA encoding important antigens for these pathogens. And the important antigen for the coronavirus infectious bronchitis virus is similar to the COVID vaccine, meaning the spike is the number one antigen. And so we want to incorporate a messenger RNA encoding that spike protein into a lipid nanoparticle and use that to vaccinate chickens. Similarly, we'd like to use the antigens of infectious laryngotracheitis, and that is glycoprotein B and glycoprotein D, to use them in an mRNA vaccine for this DNA encoding virus. So infectious bronchitis is an RNA-containing virus, and infectious bronchitis is a DNA-containing virus. So we have two models that we'd like to use for this new novel mRNA technology. And it's kind of interesting because it's basically to incorporate the mRNA in a lipid nanoparticle and using that. So instead of using a virus shell, as in what we see with vectored vaccines, we're using an artificial lipid nanotechnology. And this might sound very futuristic, but we've been using lipids to add DNA in transfections and in the laboratory for the last 30 years. So injecting a lipid nanoparticle is not a leap of faith, so to speak. And we'd also like to do this in a practical approach. So when you're getting the COVID vaccine, you're getting it intramuscularly, but we don't think that is very practical for chickens. So we want to develop the technology for in novo vaccination purposes. And another beauty of this system is that you can make you can make an autogenous vaccine for a virus that changes rapidly, and that is the spike protein of infectious bronchitis. That evolves quickly. There are new strains circulating. New strains overcome the current vaccines, and we could quickly make an mRNA vaccine for those and do it in a timely fashion compared to the inactivated viruses that are approved nowadays. So that is our basic approach.
Thank you. Your project design and methods sound really unique and novel. As you said, especially in light of the COVID-19 mRNA vaccines for humans. Can you tell us, has this approach been investigated before in poultry? And if so, was it successful or not?
No, it has not been investigated in poultry, but it has been investigated in other production animal systems. For example, we have an mRNA-based vaccine for porcine endemic diarrhea virus. And this was made by a company called ARS Vaccines, and they were acquired by Merck a few years back. So it is practical that you can do this for the veterinarian market, so to speak. And we think that it's time to look at whether or not this technology can be used for vaccination of poultry.
Wonderful. What do you see as the overall impact of this work, and do you see it leading to more mRNA vaccines for poultry viruses?
We are very excited about this technology and think we're at the beginning of a revolution in vaccinology because, you know, we were using modified live vaccines and they evolved into vectored vaccines. And now we can get rid of vectored vaccines and just use mRNA encoding the protective antigens in that technology. We're at the beginning. I frankly think that in the human field, we'll see many, many mRNA vaccines, and this technology will trickle down into the veterinary field. And I'm really convinced that these mRNA vaccine technologies have many advantages over modified lives or vectored vaccines, especially when you think about the influence of maternal antibodies interfering with protection. This, especially with the vectored or the live attenuated virus, this will never happen with these nanoparticles containing the mRNAs, because you do not build an immune response against a lipid bilayer, and it'd be great. So we finally think that if this technology can be put into place, will eliminate the headache that we see with the interference with maternal antibodies. And there's also aspects about having one shot that contains multiple mRNAs encoding different antigens. So one shot could be a bivalent, a trivalent, and this is just incorporating a different mRNAs in a lipid nanoparticle cocktail. One nanoparticle can incorporate more than one messenger RNA. And so we think that technology, and when you think about other adjuvants such as cytokines or other immunostimulating molecules, those mRNAs could be incorporated into that. So we could get a really robust and hopefully some kind of sterilizing immunity to some of these diseases.
Wow, your work sounds really exciting. And one last question for you is there anything else that you haven't shared related to this work in which the industry should be excited to look forward to?
Well, like I said, we're at the beginning of the revolution, and most things, as you know, with the COVID-19 mRNA vaccines from Moderna and Pfizer, that they had a cold chain requirement, that some of the vaccines, like I believe one was stable at -20, the other one was stable at -70, and then they said, no, it's a little more stable at -20. So the thermostability of these vaccines have to be addressed, because we really like them to be stable at refrigerating conditions. We don't really want the liquid nitrogen headache that we see with the Merrick's vaccines. So I'd like them to be more thermostable. And of course, the cost. I mean, the cost is going to be an issue with whether or not these are implemented in the vaccine industry. But like most things, costs are always getting cheaper as the technology advances. So when we were making modified live attenuated vaccines and then we vectored them, people were complaining about the cost of the vectored vaccines versus the modified live. And I'm sure they'll be complaining about the cost of the mRNA-based vaccines, but there might be niche markets, and hopefully the technology will get cheaper or less expensive, and they will be implemented. So we have faith in that. We're at the beginning of the revolution, and like most things, we have to start.
Well, that's great, Steve. And this has been a wonderful teaser for the industry to give them a little insight in this novel research that you have up and coming. And I just want to take this opportunity to thank you for taking time out of your day today to share this with us. And we will be anxiously anticipating the results and the findings.
Well, thank you. And thank you for having me here. I enjoyed this, and I look forward to the research plan, so to speak. So thank you.
Thank you.